Hello, and welcome to this video on the conservation and dissipation of energy. As we saw previously, the principle of conservation of energy states that the total amount of energy in a closed system is constant, which means that energy cannot be created or destroyed, but can only be converted from one form into another. Let's look at this football and assume for now that it's a closed system, which means that its total energy is constant. When it's held still above the ground, its kinetic energy is zero since it isn't moving, and its total energy is the sum of its kinetic and gravitational potential energies. When it's released, its stored GPE will be converted into kinetic energy, which is why it moves downwards. In a closed system, its decrease in GPE will be equal to its increase in kinetic energy, so that overall, the sum of its kinetic and gravitational potential energies remains constant. I know you might hear about this GPE to kinetic energy malarkey a lot, so what's the big deal? Well, the big deal is that our assumption that no energy was transferred away from the ball as it fell was a bit of a stretch. Most of the systems we're going to think about at GCSE aren't closed, which makes life a little more complex, but more interesting too. In reality, some of the ball's energy will have been transferred to the surrounding air particles as it fell. We say that this energy is dissipated. The word dissipate means to spread out or to waste, so energy which is dissipated is spread out or wasted. In real life, before the ball is dropped, it'll still have the same total amount of kinetic and gravitational potential energy. As it falls though, even though its GPE is still decreasing, its kinetic energy won't increase by the same amount, so it won't travel as fast, and the sum of its kinetic and gravitational potential energies at a given point will be lower. In other words, some of the GPE which the ball originally had is transferred to the surrounding air as it falls. It literally heats up the air as it travels towards the ground. In this case, the force which led to the transfer of energy away from the ball is called air resistance, but lots of other things can lead to the dissipation of energy as well. Friction between the moving parts of a machine can lead to the dissipation of energy in the form of heat. Here, some of the kinetic energy of the moving cogs will be transferred to their thermal energy store. This will cause their temperature to rise and ultimately will lead to the dissipation of thermal energy to the surroundings. The combined effects of friction and air resistance act to limit the maximum speed of a vehicle. In fact, when a vehicle is travelling at a constant speed, all of the chemical energy released by its fuel, or battery if it's a really fancy set of wheels, is transferred to its surroundings in the form of thermal energy. We know this because if the speed of the vehicle isn't increasing, then its kinetic energy store isn't increasing either, so all of the energy being supplied to it must be getting dissipated in less useful forms. Energy dissipation isn't always a bad thing though. It's what allows us to decrease the kinetic energy of a car to bring us safely to rest. As it takes off, the chemical energy from the fuel of a plane is being used to increase its kinetic and gravitational potential energy stores, but again, due to the effects of air resistance and friction, some of this energy will be dissipated to the surrounding air. Energy dissipation also occurs in electric circuits. Due to the electrical resistance of this circuit, not all of the chemical energy which is supplied by the battery will be converted to useful light or electromagnetic energy in the bulb. Quite a lot might end up being dissipated as heat. Less so though if we're using an energy-saving light bulb, but more on that later. Of course, even useful heat energy can be dissipated. There's nothing like sitting around a campfire with a few friends, but don't sit around for too long, because all of that lovely thermal energy that's being released by the fire will quickly be dissipated into the surroundings. Even when things aren't on fire, they'll still lose thermal energy to their surroundings by the processes of conduction, convection, evaporation, and as shown in this infrared image, radiation. If all this talk of everything and everyone losing energy all the time is too much, don't worry. There are lots of ways to reduce the dissipation of energy from a system. Lubrication, using oil or other liquids, reduces the friction between the moving parts of a machine. Using wheels decreases the friction between an object and the surface over which it's moving. Streamlining vehicles reduces the amount of air resistance exerted on them. In an electric circuit, using low resistance cables reduces the amount of energy dissipated as heat. And finally, adding thermal insulation to a building reduces the rate at which thermal energy is transferred away from it. Because it's a pretty important one, And because examiners are pretty keen on asking about it, we're going to talk about this last point in a little more detail. What a lovely house. If it wasn't just a cartoon, then it would probably do me well. But what are all those nasty arrows about? The arrows represent the transfer of thermal energy away from the house. The thicker the arrow, the greater the amount of energy lost from that part of the house. As we can see, loads of energy is lost from the walls of a house. Clearly, building thicker walls will help, but the best way to reduce the loss of energy in this way is by using cavity wall insulation. Most modern homes have cavity walls, which means that they have double walls with a gap in the middle like this. By pumping insulating polystyrene foam into these gaps, we can reduce the rate of loss of heat energy from the house. Polystyrene foam is an excellent insulator, which means that it's a poor conductor of thermal energy. We say that it has a low thermal conductivity. The lower the thermal conductivity of a material, the lower the rate at which heat energy will be transferred through it. So materials with a low thermal conductivity are good if you want to keep your home warm. Moving on, thermal energy is also lost from doors and floors. Installing draft excluders, carpets and floor insulation can help conserve energy. Double or triple glazing also reduces the loss of heat energy from a house. Air also has a low thermal conductivity. It's a good insulator, so having an air gap between the panes of glass in a window also helps conserve energy. Lastly, the large amount of energy that can be lost through the roof of a house can be reduced by the installation of loft insulation in the form of thick felt or fiberglass. Efficiency is a word that's used a lot in everyday language, but in physics, as you might have guessed, it has a very specific meaning. The efficiency of a system or process is the ratio of the useful output energy transfer to the total input energy transfer, or the ratio of the useful power output to the total power input. We can calculate the efficiency of a system or process using this equation. Efficiency equals useful output energy transfer divided by total input energy transfer, or we can use this version instead. Efficiency equals useful power output over total power input. Because the right-hand side of each of these equations is a ratio, efficiency doesn't have a unit. Efficiencies can be quoted as a decimal from 0 to 1, or as a percentage from 0 to 100%. Let's go through a couple of examples to make sure we're happy with using these equations. Example 1, and we can see that the total input energy here is 120 joules, and the useful output energy in the form of kinetic energy is 30 joules. To work out his efficiency, we use this equation, and then subbing in our numbers, that becomes 30 divided by 120 to give an answer of 0.25 as a decimal, or as a percentage, 25%. Part B now, and hopefully you'll see that the chemical energy which isn't converted to kinetic energy will be transferred to the thermal energy stores of the boy, the path, the surrounding air, and so on, which may cause their temperatures to increase. Example 2 is a bit trickier. As you can see, a 5-watt electric motor with an efficiency of 10% is being used to lift a 400-gram load. In part A, we're looking for the amount of energy transferred from the motor to the load each second. So where do we start? Well, where we start is by realizing that a power of 5 watts tells us that the motor is transferring 5 joules of energy per second. Of this, only 10%, or 0.1 as a decimal, is transferred usefully to the load. You might see right away that that means that 0.5 joules of energy is transferred to the load every second, but if you did want to do things by the book, you would start by writing down the efficiency equation, then rearranging to make the useful output energy the equation, and subbing in our values, that becomes 0.1 as a decimal, times 5, to give our answer of 0.5 joules every second. Part B is actually easier than it looks. We know that, as the load is lifted, its gravitational potential energy increases. Our equation is EP equals mgh. Subbing in from the previous answer, 0.5 joules equals the mass, which is 0.4 kilograms, times 9.8 times h. Our next line looks like this, 0.5 equals 3.92 times h, which gives a value for h of 0.128 meters. What this means is that the load moves up by this distance every second. Since speed is just the distance something travels in 1 second, that means that our final answer is 0.128 meters per second. The required practical activity for this part of the course involves investigating how effective different materials are as thermal insulators. Remember that a thermal insulator is a material which has a low thermal conductivity, and a thermal conductor has a high thermal conductivity. There are a number of ways in which you could carry out this investigation, but one of the easiest and most effective ways is as follows. Wrap a beaker in an insulating jacket, like this aluminium foil, pour in some hot but not boiling water, place a lid on top with a hole in the middle to allow the temperature of the water to be measured using a thermometer, and then measure the decrease in the water temperature over a set period of time. You can then go on to see how changing the insulator used affects the temperature decrease of the water. Hopefully you'll see that the independent variable in this investigation is the type of insulator used. This is a categoric variable. The different types of insulators used fall into different categories which can only be described by words and not by numbers. The dependent variable is the temperature decrease of the water. Changing the independent variable, the type of insulator used, affects the temperature decrease. Finally, to ensure that our investigation is a fair test, we'll have to ensure that all of the other variables that could affect the results of the investigation are kept fixed as control variables. We'll want to use a measuring cylinder and a stop clock to ensure that these two variables in particular are properly controlled. Typical results from this investigation might look something like this. As you can see, we've plotted a bar graph here because the independent variable, the type of insulator used, is a categoric variable. For this investigation, we've used a thermometer with a resolution of 1 degree Celsius. The resolution of a measuring device is the smallest change that it can measure. An electronic temperature sensor might have a resolution of 0.1 degrees Celsius. That's 10 times better than our old thermometer. Do you think that using a temperature sensor in place of a thermometer would have changed the results of our investigation? That brings us to the end of this video on the conservation and dissipation of energy. If all of your chemical energy hasn't dissipated by now, why don't you try the exam style questions for this topic?